Hi, this is Surely Physics, episode on vector notation and addition. Welcome. I'm going to switch over. A vector is a quantity with both magnitude and direction. So it can be represented by an arrow. So this is an arrow. It could be a vector if it represents a force or velocity or something like a displacement, anything with an amount and a direction to it. Your age or time or your weight, your mass has no direction to them. So hopefully your life has direction, and that's why you are watching Surely Physics. Is your life a vector? That may not be a discussion for this class, perhaps another one. But things like forces and displacements and velocities are. So force, for example, could be an amount to the right, like this vector might represent, and it may be 10 newtons or 10 pounds, might have a magnitude of 10. If I add another vector to it, we get into the realm of vector addition. And this is one concept we're going to be looking at later. For example, if I walk or hike 10 miles to the east and then 10 miles south, how far away am I from the starting position? And this is the kind of question that vector addition can answer. Now, if we put that together, you might start to see a right triangle. So, of course, Pythagorean theorem would apply here. So these are all the uses for vectors, and that's what we'll be looking at in this lesson. Now, a vector has a notation to it. This would represent vector A. Writing an A by itself may be just a magnitude, but putting the little half an arrow sign, I'll call it half an arrow, on top of the A gives it the notation of a vector. Now, vector A might have a length of 10. Now it could be 10 miles, so I'll write miles. So that might be a displacement vector. But it's not a vector yet because it needs to have a direction to it. And if I add east, now it has a direction. This is a vector. I might also have vector B. And if vector B is 10 miles south, now we've defined those two vectors A and B, and I can label them on this diagram. Vector A and vector B. There we go. In a textbook, you may see A and B bolded, where the other variables around them are not bolded. So sometimes you'll see that if there is not a notation on it. All right, so what would be the addition of A plus B? Now, looking at this, if these are labeled with miles here, what we're looking for is the hypotenuse of this triangle that we've created with A and B. Now, if you know your triangles pretty well, you might have a good answer for that. So A plus B, what do you think? Well, we take the square root of 10 squared plus 10 squared, and we would get our answer out of that. And so that, what is that, about 14? So around 14 miles would be the length of that. Now, is it a vector yet? We are looking for a new vector. When you add two vectors together, you get another vector. So what would this direction be? So we would have to look at the angle now. Now, if this were anything other than 10 and 10, we could use the tangent. To find theta, you might say the angle theta would be the inverse tangent of the opposite over the adjacent side. And that will give you the hypotenuse. But of course, if you take inverse tangent of 10 over 10, you get inverse tangent of 1, which is 45 degrees. And our angle here should be 45 because our two lengths are the same. You can try that with any other triangle that might have different sides and you'll get a different angle. If they have the same sides, you'll get 45 degrees out of that. If you're a radians person, of course, you can use pi fourths. There we go. All right. So this might be nothing new. It might be like, oh, Mr. Shirley, it's like we've done this kind of stuff before. What's the use of it? Well, what if you go on a more complicated hike where there's a 10-mile east and a 10-mile south direction change. But then what if you go to the northwest, 8 miles? Okay, so now we'd have a third vector in here. And I almost made this a long vector, and I'll use my accidental mistake here to talk about something. If I try to indicate an 8-mile vector, I should put it in proportion to my other two. So this vector, this ugly looking one here, would be way too long. So let's undo that. An 8-mile vector should be shorter than those 10s in appearance. And we're not making a perfectly scaled system here. But northwest would be a 45-degree angle. And what if we then turn, let's say, 20 degrees east of south? Now that's a new direction, 20 degrees east of south. And we go, let's say, 5 miles. So what I'm going to do here is make a new vector, 5 miles, where this little angle in here is 20 degrees. Okay. Now, east of south, let me talk about that. 20 degrees east of south, and this is how you can write it, E of S. This is talking about 20 degrees toward the east of the southerly direction. And that's a convention of talking about direction. If you have the cardinal directions, northeast, southwest, 20 degrees east of south would be in this direction. This same angle could also be stated 70 degrees south of east. That would indicate the same exact direction. Generally, you'll take the smaller angle, whatever's closer to 0, and that's the easier way to write it. So 20 degrees east of south or 70 degrees south of east would be the same exact angle, because 70 degrees, of course, would be this one toward the south of the east direction. Just going to clean that up a little bit. Okay, so what if we have these 4 different directions? Where are we going to end up? It becomes a little bit more complicated. So when you've got several vectors like this and you need to add them up, you could do a large construction. You could say, okay, we go 10 miles to the east, and then if we add these 2 vectors together, you add vectors by putting tail to tip. All right, tail to tip. So we'd have a 10, and the next one, a tail to tip, was an 8 in the northwest direction. And then we had 5 miles, 20 degrees east of south. So if this is south, we're going to have a 5 sort of like that. Poink. X marks the spot. So that would be the end point. And our final displacement, if we add all those up, would be the distance from here to here and the direction. Let me just change color a little bit. We would have a vector starting from our starting point and going to our ending point. All right, well, that's kind of small and difficult to look at. So what exactly is that amount? What is the length? We're not talking about an easy Pythagorean theorem problem here. So what we're going to do is convert these vectors into their I, J, K components. And what a component is a piece. So the vector A, instead of being written 10 miles east, we could say it is 10 in the I hat direction. And that's how you say that. It's a lowercase I, but instead of putting a little dot above it, you say hat. And what this is a unit vector. I hat is a unit vector in the X direction, in the horizontal direction. So think about a coordinate plane, the X direction would be the I hat direction. It has a magnitude, let me undo that, of 1. It is a vector, okay? We're not writing the same vector notation here. We're using a different piece of vector notation called the hat. It indicates this is a unit vector, is a magnitude of 1. Let's Still getting used to this pen. And a direction of the x direction. So what do you think negative I direction would be? That would be the negative x direction. So this is actually a complete vector notation way to describe A. Instead of 10 miles to the east, if we define right, the positive x direction as east, as you would see a cardinal plane or a compass rose, that type of thing, this would be appropriate. And how about 10 miles south? What do you think B can be described by? We have 10 miles south. We have a magnitude of 10. And what would go over here? Would it be a I or negative I? No, guess what? It's a J, J hat. But since it's south and positive y direction is generally up in the north direction, we could put a negative on the front here. Or another way to write this is a positive 10 in the negative j direction. This is actually more accurate, showing that the negative applies to the direction. Okay, so the magnitude could be a negative with a positive direction, or the magnitude could be positive with a negative direction, and you'll still get a negative 10 j hat. All right, so what about these other two vectors? We'll call this vector C. And how would we describe that if it has a magnitude of 8? All right, now this vector, we're going to have to break it up a little bit. And sometimes breaking it up and doing a little work ahead of time helps make a larger problem a little bit more simple. So here's an 8, and we do have a direction here of 45 degrees. This was to the northwest. So we do have a 45-degree angle. So what we're going to do is find the components, the I and the j components of this new vector C. Okay, we'll call it vector C. And we do that by extending a horizontal line over. This will represent the horizontal component, and from there extend a line up. Think of it like in your head, the beginnings of like an axis. We got the y and the x-axis. Okay, it would really be extending from the start here. So this will be in the negative x direction and a positive y direction we'll see in the end. So if we make this kind of triangle, and you might be able to see it if I use some blue here, it makes a nice triangle. Okay, it's a right triangle. Therefore, we can use sines and cosines. So with this right triangle, this component down here will have a magnitude of 8 cosine 45. If you're going, Mr. Shelley, where are you pulling this from? Just recall the definition of a cosine of an angle is the adjacent side divided by the hypotenuse. Okay, so if we were looking for the adjacent side to the angle of 45 degrees, we would have cosine 45 equals our unknown adjacent side divided by the hypotenuse, and that value, that magnitude, is 8. So if we multiply both sides by 8, the 8 would cancel over here, and we get an 8 in front of our cosine 45. So that's the origins of the 8 cosine 45. And likewise, we'd use a sine function over here to reveal that the vertical component here is 8 sine 45. All right. Now, what we can then do is label C. C is ready to go. In the x direction, there's a negative. Let me switch back to black here. Undoing. Okay. I had undo difficulty. All right. We'd have an 8 cosine 45, and you generally write the x direction first, x, y, z. You can look into three-dimensional vectors, by the way, and we won't do that today. But this is in the negative I direction, negative x direction. Then we'll also have an 8 sine 45, and that is upward in the positive j direction. Okay. Whew. And finally, we have this vector D. Likewise, we're dealing with an angled vector here. So if you break this up, create a new component diagram here. There's the y component, and the x component is going to be smaller. There's the angle, and the magnitude is 5. You'll see from this angle, this 20-degree angle, the horizontal component isn't the cosine. The cosine component goes along with the vertical piece here. The vertical piece is now adjacent to this angle. So the horizontal component will be 5 sine 20 in this case. I keep hitting the eraser button. There we go. And the vertical piece is 5 cosine 20. There we go. And we'll just bring that over here. What goes in the x direction? We're going to have an x direction is to the right. That's positive 5 sine 20. That's in the positive I direction. And we're going to have a 5 cosine 20 in the negative I direction. So 5 cosine 20. Sorry, I meant to the negative j direction. Okay, so negative j. So there we go. We've got 4 vectors. And we're ready to add them up. Scroll down a bit. How do we get the sum of all these vectors? A plus B plus C plus D. You add them just like you would an expression with x and y. If you've got 2x plus 5y, and you add to that 4x minus 6y, you would add the 2x and the 4x together to get 6x. And likewise, you would add the y pieces, those y terms as well. These I and j components create terms that you can add and subtract. So adding these together in a big, large expression would be 10i minus, this would be vector b, negative 10j. Now we can't add or subtract those two from each other. We'd have to leave them like that if we were just adding a plus b, because they're different terms. I and j are those different terms. And then we'd have c coming along. I'm going to bring the negative out to the front. So minus 8 cos 45. And of course, we could simplify that to a number. And then plus 8 sine 45. So that together is, put that on the wrong place. Be careful with your parentheses. You could add, you know what, I'm just making this uglier. This whole piece here is vector c that we're adding. And then we're going to add vector d, 5 sine 20 in the I direction. And look at that, I left this off. We need an I here and a j here. A lot to handle. And a negative 5 cosine 20 in the j direction. So at this point, you combine like terms, add up all the i's, add up all the j's, and you'd have your result. We're going to try out a cosine, 8 times cosine 45. So we'll start with 45 and our cosine. Multiply that by 8. That's 5.66. Okay, so we're going to have a 10i minus 10j minus 5.66 I. And then sine of 45 is the same as cosine of 45. So we're going to have a plus 5.66 j. All right, then we've got this 5 sine 20. So we're going to take a 20 now. So you have a better calculator than me on the screen here. And multiply that by 5. You get a 1.71. Okay. So it's a small piece of that. 1.71 I. And then minus 5 cosine 20. I guess I need that again. 20 cosine. 0.93 times 5 is 4.3 698. I'm just going to say 4.7. All right, so we got a 4.7j. All right, now we're going to combine all those like terms. We've got a 10i minus 5.66 and plus 1.71. Let's just tally that up here. 6.05i. And finally, we're going to take that negative 10 and a negative 9.04. There we go, in the j direction. So our final vector has these two components. You got an x component in the positive x direction, and you got a negative component in the y direction. And look at our red vector up here. This is our little sketchy vector up here. It is in the positive x direction. In the negative y direction, you can see that there's more y than x. So it looks like our numbers down here agree. How do you get the amount? Well, you can take the Pythagorean theorem and use that. Square root of 6.05 squared plus negative 9.04 squared. And you'll get the magnitude of this. And then you can take the inverse tangent. This is the y component. So you can take the inverse tangent of 9.04 over 6.05. And that would reveal the angle right in there. Okay, that'll give you an angle for your new vector. So some kind of complicated vector system here can be simplified by taking the components of those strange angled vectors and summing them up. So in this video, you've seen vector notation in the IJK form. You've seen addition also in some scenarios where we would add different vectors together. So these vectors could be added in terms of displacements or forces or whatever quantities have directions. So I hope this video has been helpful.